So thank you all for allowing me to speak a little bit today about our project that's a collaborative activity to try to build a really strong proposal for Phase 2 funding from the Gates Foundation. So the project in particular is to develop Inkjet imprinted paper for poliovirus detection and differentiation. And essentially the goal of this project is to try to make paper-based, low-cost sensor technologies. And in particular, we're applying it to the detection of poliovirus. And for the developed world, poliovirus really isn't that big of a challenge. But if you're going to lesser developed parts of the world, polio still is a disease that actually is replicated and moves through the environment. And so there's interest by the Gates Foundation to try to understand the processes which lead to its movement in environmental samples. And just schematically, what we're essentially trying to do is we're trying to make little pieces of paper, and Matt has one right here that he can pass down the rows, where effectively we are going to apply a sample that we think has poliovirus to it, and we want to be able to monitor whether or not this virus is present within the sample. And in particular, we want to try to do this using surface-enhanced Raman spectroscopy because we think that it gives us a very fine degree of sensitivity. So just to take you through the project as it stands today, we've essentially spent a lot of time trying to figure out how to make different types of paper-based substrates. And that piece of paper that I've passed out is essentially just a piece of filter paper. And what we are doing with it is we are printing on it with a wax printer. And this is literally what our wax printer looks like. It is very similar looking to a laser printer, but instead of printing ink, you print wax. And when you do that, you then, after you've done that and you've designed what your substrate is going to look like, you heat it on a heat plate or in an oven, and essentially the wax melts and you end up producing a hydrophobic zone that paper can't, or your analytes can't go through. So we can then apply our sample, and then we can examine them either by eye if we're looking for something that is easily seen visually, or we can do it using Raman spectroscopy. So we can characterize our samples, and we've done a lot of this out at NCFL, essentially looking at whether we've got wax on the paper, heat the wax, what happens to the wax. And just looking at what I passed out was an unheated sample. But once you heat it, the wax spreads, and so you end up changing some of the zones. And we've spent a lot of time trying to define exactly what the proper size of our substrates should be. So just to kind of cut to the chase, we've been able to show that our Raman-based methods actually allow us to see things present within the paper. This is not actually for poliovirus, but this is for a aquatic algae piece of capitata. And essentially what we have done is we apply a sample containing this algae to this kind of circular zone that's on the right side of these images. And effectively we can watch the transport by capillary flow of the piece of capitata. And we can actually see exactly where it is relative to our flow channels and relative to the paper. So we've spent a lot of time, and this has been the major focus of everything that we've done so far, trying to understand the characteristics that affect transport of our analytes in a wax imprinted channel. And most of our work has not yet been done with viruses because that takes a lot more effort in terms of preparation and everything else. And instead we've been focusing on soluble chemicals, and we've been focusing on nanoparticles, with the nanoparticles acting as surrogates for viral particles. So essentially what we do is we apply sample to our application zone down at the bottom of each one of these flow channels, and we're observing what happens to it. And this is for a amaranth dye. And amaranth transports pretty well. You can see that in the images over to the left, but it also, and it's a little harder to see in this room, but it also partitions very effectively to the wax channel, which makes sense because the wax is going to be hydrophobic. Amaranth has a lot of hydrophobicity associated with it. So there's a partitioning process that occurs. We've spent time, as I said before, really characterizing particle flow. So we're interested in how particles such as poliovirus transport. And effectively, we've done studies with water-soluble materials, gold nanoparticles, silver nanoparticles. And effectively, the take-home message from all of this that we've done so far is essentially to tell us that water-soluble things transport more effectively than things that are less water-soluble. But there's some interesting chemistry that goes on, and we're spending time trying to characterize the details of that chemistry. And effectively, we're looking at citrate coatings, polyethylene glycol coatings, we're looking at DNA aptamer coatings, and they all have slightly different effects. So we can think about what the variables are in this system that affect how well a particular paper-based substrate is going to work for the analysis of different types of analytes. And the things that we have to consider are what's the size and the shape of our analyte, what is the surface charge of the analyte, how polar is it, is it highly water soluble, is it not highly water soluble, how does it associate with the wax or not, what is its aggregation state. If we're dealing with environmentally relevant samples, we're going to have viruses that are going to be sometimes all clumped together, and those are going to transport differently than viruses that are more well dispersed. So just to wrap up, essentially we have developed a platform where we have a fairly good understanding of what the different characteristics are that affect where things actually transport within these columns. And we've done this using nanoparticle circuits. And we're now in the process of, we're going to start working actually with poliovirus. And we have collaborators at the University of Michigan and at Stanford University and at EPFL in Switzerland that are providing us with the poliovirus and providing us with some of the characteristics of those. And so we're doing that, and then at the same time we're also doing kind of a side project with some of our ICTAS funds to impregnate our filter paper actually with gold nanoparticles in the first place. And so we're actually producing the particles inside of the paper. And the point in doing that is so that we can suppress any background fluorescence that might have existed with paper by itself. When you do Raman-based methods, fluorescence is always a problem. So if we have gold particles that are there in the first place, that suppresses that. In terms of where we go in the future, we've got our Gates Foundation Phase 2 proposal, which is going to be due November 1st. And then we're also looking at a NSF biosensors proposal that will be due this coming fall. And with Lindsay and Elukan Kumaran, we're looking at trying to translate this to other types of environmentally relevant matrices, whether it's air, as well as other environmentally relevant viruses.